At 7:34 on the morning of August 10, the ground beneath western Colombia began to move. A magnitude 7.4 earthquake had struck near San José del Palmar in Chocó. In city after city, people ran into the streets. Buildings cracked. Some partially collapsed. Others only meters away remained standing. That difference can look like luck. But inside an earthquake-resistant building, almost nothing is left to luck. The soil beneath it, the shape of its floor plan, the position of its walls, the steel hidden inside its concrete, even the way its ceilings and pipes are attached, all of it determines what happens in the few seconds when the ground stops behaving like solid ground. So today we are going to design one building from the ground up, a structure intended not to remain perfectly undamaged, but to do the one thing that matters most during a major earthquake, not collapse. The Colombian Geological Service placed the earthquake at a depth of 103 kilometers. The United States Geological Survey calculated 107. At that depth, this was not a shallow rupture directly beneath a city. Yet its enormous release of energy allowed the shaking to travel across a wide area. The event was felt throughout much of Colombia and beyond its borders. The Colombian Geological Service received more than 12,000 felt reports from roughly 900 population centers on the first day. The maximum reported intensity reached level 7 on the European macro-seismic scale, a level associated with severe damage. But magnitude alone does not tell us what any one building experienced. The motion at a site depends on the depth and location of the rupture, the path the seismic waves follow, the local soil, the duration and frequencies of the shaking, and the building itself. Think of an earthquake as music played through a city. The source creates the sound, but the ground acts like a speaker, and every building responds like a different instrument. If the frequencies line up badly, motion can grow. If the structure has a hidden weakness, that motion can concentrate in exactly the wrong place. Investigators are still determining why individual structures failed in Colombia. It would be irresponsible to announce one universal cause now. What we can do is examine the design decisions that have repeatedly separated collapse from survival in earthquakes around the world. And the first decision is made before a single column is poured. Our hypothetical building will be 8 stories tall. Before drawing its structure, engineers need to know what is beneath it. 2 sites in the same city can experience different motion. Solid rock often transfers shaking differently from deep layers of soft sediment. In some settings, soft soil can amplify particular frequencies. A building that appears far from the epicenter may still be strongly shaken if the local ground and the incoming waves interact unfavorably. Then there is liquefaction. Loose, water-saturated sediment can lose much of its strength during intense shaking. The ground does not literally become water, but it can temporarily stop supporting foundations in the way engineers expected. Buildings may settle, tilt, or move sideways even when their structural frame remains largely intact. So the design begins with boreholes, laboratory tests, groundwater measurements, and a site-specific understanding of seismic hazard. Engineers estimate how the ground may move and whether it could settle, spread, slide, or liquefy. Only then can they choose a foundation. On competent ground, a mat foundation may distribute the building's loads over a broad area. At a more difficult site, deep piles may transfer forces toward stronger layers below. Other projects may improve the soil itself through densification, drainage, grouting, or stone columns. There is no foundation that is automatically earthquake-proof. A deep pile driven into the wrong layer is not a solution. A massive slab placed over unstable ground is not a solution. The foundation, soil, and building must be analyzed as one interacting system. For our building, the geotechnical investigation finds a deep layer of softer material above stronger bearing strata. The engineers select a foundation system suited to that profile and account for the motion expected at the site. Now the building has somewhere to stand. Next, it needs a path for the earthquake's forces to reach the ground without tearing the structure apart. An earthquake does not simply push a building over from the side. The ground moves first, the foundation follows. But the mass of each floor resists that sudden change in motion. That inertia creates horizontal forces throughout the structure. Every one of those forces needs a continuous load path. The floor slabs act as horizontal diaphragms. They collect seismic forces and transfer them to the vertical elements designed to resist side-to-side motion. Those elements may be reinforced concrete shear walls, steel braced frames, moment-resisting frames, or a carefully engineered combination of systems. From there, the forces travel through the foundation and back into the ground. If one link is missing, the load does not disappear. It searches for another route, often through parts of the building that were never intended to carry it. Imagine carrying a heavy suitcase with a chain. Thick steel links will not help if one connection is made from thin wire. During an earthquake, the weakest connection can control the behavior of the entire building. So our design uses a reinforced concrete core around the stairs and elevators, supplemented by moment frames along the exterior. The core supplies stiffness. The frames provide additional strength and redundancy. The floor slabs connect the two systems. But strength must be distributed in both principal directions. A building designed to resist motion only from east to west remains vulnerable when the ground moves north to south or along both axes at once. The connections matter just as much as the members. Floor-to-wall connections, beam-to-column joints, collectors, anchors, and foundation ties must all survive repeated reversals of force. That gives our building a complete skeleton. But even a strong skeleton can be defeated by the wrong shape. The safest seismic designs are often easy to read. When mass and stiffness are distributed relatively evenly, the building's motion is more predictable. When they are badly offset, the structure may twist as well as sway. This is called torsion. Irregular buildings can still be engineered safely. An L-shaped tower, a curved hospital, or a complex mixed-use project is not automatically dangerous. But irregularity demands more analysis, more careful detailing, and sometimes seismic joints that allow different sections to move without pounding into each other. The more dangerous irregularity may be one that is almost invisible in photographs, a sudden change from one floor to the next. Picture an apartment building with masonry walls on every residential level, but an open ground floor for parking or storefronts. The upper stories are relatively stiff. The open level below is flexible. During strong shaking, displacement can concentrate in that single story. That is the soft story problem. It is not the presence of cars or shops that creates the danger. An open level can be designed safely. The problem begins when the ground floor does not have enough lateral strength or stiffness for the demands placed on it. In our building, the architect wants a completely open lobby. The structural model shows that this would concentrate drift at the first story, so the team changes the design. Portions of the concrete core continue all the way to the foundation, and additional frames are placed around the lobby perimeter. The space still works. But the seismic system is no longer interrupted at the level carrying the weight of every floor above. This idea is fundamental. Do not allow one story, one column line, or one connection to absorb the entire earthquake. Spread the demand, create redundancy, make the building deform as a system, and then prepare that system to be damaged without suddenly losing its ability to stand. This may be the most counterintuitive part of earthquake engineering. A good building is not designed to remain perfectly rigid under every possible earthquake. If a structure cannot deform, it may break suddenly. Engineers instead give it ductility, the ability to bend, yield, and dissipate energy while maintaining enough strength to avoid collapse. Consider reinforced concrete. Concrete is strong in compression but weak in tension. Steel reinforcement carries tension and helps hold the concrete together. Yet simply placing steel bars inside a column is not enough. During an earthquake, forces reverse again and again. The concrete cover may crack and spall. Longitudinal bars may try to buckle outward. Closely spaced transverse reinforcement, often called ties or hoops, confines the concrete core and restrains those bars. The detailing becomes especially important near beam column joints and potential hinge zones where cyclic demands can be severe. Engineers also apply a principle commonly described as strong columns and weaker beams. That phrase does not mean weak beams in the everyday sense. It means the system is proportioned so that under extreme loading, controlled yielding is more likely to occur in selected beam regions before a story-wide column mechanism forms. Why sacrifice parts of the beams? Because a beam hinge can absorb energy while the columns continue supporting the building's weight. If columns throughout one story lose their capacity first, the floors above may descend together. The goal is a hierarchy of behavior. Some components are allowed to yield. Others are protected. Brittle failure modes, such as sudden shear failure or a poorly detailed joint breaking apart, must be prevented from occurring first. This is called capacity design, deciding not only how strong a building should be, but where it may yield and how that yielding will unfold. In our building, computer analysis identifies the regions of highest demand. The engineers adjust member sizes, reinforcement, joint details, and confinement. Then they check story drift, stability, and the effects of repeated cyclic motion. The finished structure may crack in a major earthquake. Some areas may need extensive repair. But cracking is not the same as collapse. The building's most important safety feature is not that it never moves. It is that its movement has been anticipated. For many ordinary buildings, a well-designed conventional seismic system is enough to meet the required safety objective. But some structures need more. Hospitals, emergency centers, data facilities, bridges, and high-value buildings may be designed not only to avoid collapse, but to limit damage and recover function quickly. One option is base isolation. Instead of connecting the building rigidly to the moving ground, engineers place specially designed bearings or sliding devices between the structure and its foundation. These isolators lengthen the building's period of vibration and reduce the acceleration transmitted into the floors for the motions they are designed to address. The building still moves, sometimes by a considerable distance at the isolation level. Flexible utility connections, separation space, and restraints must all be designed for that displacement. Another option is added damping. Viscous dampers yielding metal devices or other energy dissipation systems act somewhat like shock absorbers. They convert part of the structure's motion into heat or controlled deformation, reducing the demand on primary structural members. Neither technology is magic. Isolation has limits. Dampers must be placed and sized correctly. Both require specialized engineering, inspection, and maintenance. Our apartment building does not automatically need these systems. But if the project were an essential hospital expected to operate immediately after a disaster, the performance objective would be higher, and isolation or added damping might become economically justified. That distinction matters. Building codes generally establish minimum safety requirements. They are not universal promises of zero damage, zero downtime, or zero loss. To keep a building operating, engineers must protect far more than its concrete and steel. A building can remain standing and still become dangerous or unusable. Ceilings can fall, facade panels can detach, glass can break, unbraced mechanical equipment can slide, sprinkler pipes can rupture, water tanks can shift, elevators can stop, a fire can begin after the shaking ends. These are called non-structural components, not because they are unimportant, but because they are not part of the primary gravity or seismic frame. In many buildings, these components represent most of the economic value. In a hospital, their failure can erase the benefit of a frame that performed exactly as intended. So our design anchors equipment, braces suspended systems, provides movement-compatible facade connections, secures tanks, and gives pipes enough flexibility to accommodate story drift. Heavy contents are restrained where necessary. Emergency systems are arranged so that one local failure does not disable the entire building. The same principle applies at home. A tall, unanchored cabinet, a water heater, or heavy objects stored above a bed can become a serious hazard even when the building itself is safe. But there is an important line between securing contents and judging a structure. After an earthquake, a visual checklist cannot certify a building as safe. Do not enter a structure that has been cordoned off or visibly damaged. Cracks, leaning walls, displaced columns, unusual sounds, jammed doors, or falling materials justify leaving the area and seeking an official professional inspection, not conducting a personal investigation inside. The building is now complete, but most people in an earthquake do not live in a newly designed structure. They live in one built years or decades before the latest lessons entered the code. An older building is not automatically unsafe, and a newer building is not automatically safe. Age is only one clue. What matters is the code used, the original design, the quality of construction, maintenance, corrosion, damage, changes in use, and modifications made over the building's life. Removing a wall, cutting through a slab, adding heavy rooftop equipment, enclosing openings, or changing a ground floor can alter how forces move through the structure. A change that appears architectural may have structural consequences. Seismic evaluation begins with drawings, site conditions, material testing, inspection, and analysis. If weaknesses are found, retrofit options may include new shear walls, steel-braced frames, reinforced concrete or steel jackets around columns, stronger connections, diaphragm upgrades, foundation work, or ground improvement. The correct intervention depends on the actual weakness. Adding concrete in the wrong place may only add mass. Adding a very stiff wall without understanding the rest of the system may shift forces into an unprepared foundation or create a new torsional problem. A retrofit is not a collection of repairs. It is a redesign of the building's path through an earthquake. Colombia has required earthquake-resistant construction through the NSR 10 regulation and related laws, while officials continue working on updates. But regulations protect people only when engineering, permits, materials, construction, inspection, maintenance, and later alterations all remain connected. A code exists on paper. A safe building exists in concrete, steel, soil, and thousands of decisions made correctly. Now the ground moves beneath our finished building. The foundation transfers the motion. The floors gather inertia forces. The core and frames carry them downward. The building twists only within the limits anticipated by the design. Reinforced zones confine the concrete. Selected components yield and dissipate energy. Ceilings, pipes, tanks, and facade connections accommodate the movement. When the shaking stops, the building may not be untouched, but it is standing. That is what earthquake resistance really means. Not defeating nature, not promising that nothing will crack. It means controlling how damage develops so that a violent release of energy does not become a sudden structural collapse. The August 10 earthquake is now part of Colombia's seismic history. The Colombian Geological Service described it as the country's largest recorded earthquake of the 21st century. But the engineering history of this disaster will take longer to write. Investigators must examine the ground motion, the soil, the age and design of each structure, its materials, its construction, its maintenance, and every alteration made afterward. Only then can individual failures be explained responsibly. Earthquakes cannot yet be predicted with useful precision. Collapse, however, is not always unpredictable. Long before the ground moves, a building's behavior is being shaped in the soil report, in the structural model, at every connection, and on every construction site. The earthquake lasts seconds. The decisions that determine survival are made years before it begins.